Euclidean K-median and K-means, I think.
All right, thanks, Julian, for the intro, and thanks for the workshop and program organizers for putting together a great program. Yeah, so I'll be talking about well, this thing right here. And the goal is very humble. All we want to do is just cluster a stream of endpoints in space that's little o of log n. Yeah, so actually, I don't think that in spite of all of the talks so far, we've actually introduced clustering. So let me just give a brief introduction, even though a lot of you guys are probably familiar. OK, so we have an input data set X. That's what appears on the left of your screen. And the goal is to partition X so that some notion of similar points are in the same cluster and different points are in just different clusters. Okay, there are a lot of ways to do this, but the notion that we'll consider is called K clustering. And that's just where there's a fixed number, K, of clusters that we want to partition the data set into. Okay, so for K equals 3, the natural partitioning would be into the 3 clusters right of your screen. Okay. All right, so there are many ways to measure the quality of each clustering. The way we're going to do it is that we're going to assign a center to each clustering, to each cluster in the clustering. And then we'll have a cost function that's induced by the center for all the points in the partition Pi that's assigned to Ci. Okay. So we're going to assume in this talk that the points are living in some metric space with a distance function. And for each cluster of points, so Pi is a group of points, the cost induced by Pi due to the center, Ci, is going to be some function of the distances of the points in the cluster to the center. Okay. And then more generally, the overall clustering cost is going to be a function of the costs induced by each partition. Okay, so this is the overall clustering cost. We have a set of centers C. There are K centers here. X is our data set. So this is a function of the overall sets of distances. Okay, pretty standard stuff. So just as a quick illustration, let's suppose that we have a set of points. Okay. And there's only one center. Then the common K center metric is just we take the largest distance between the center and some point. K median is the sum of the distances. K means is the sum of the squared distances, and KZ clustering is sum of the zth powers, right? And of course, you can see that for z equals 1, it's K median, z equals 2, it's K means, so on and so forth. Okay. And again, just to simplify things, what we're going to be doing in our talk is just considering Euclidean K clustering. So we'll have endpoints that are in d-dimensional space, but furthermore, they're actually between 1 and delta. So they're integers between 1 and delta. And you can think of delta as some kind of aspect ratio or accuracy or granularity, so that if your input isn't all integers, you can round down, or like bit precision, you can round down or scale down so that everything's a multiple of some integer. Okay, and since we're in the Euclidean distance, we have the standard L2 distance for the distance function. Right, so in summary, this is the problem that we're going to be looking at. OK, so that's clustering. And I promised you that I would be looking at something in the streaming model. So here's the streaming model. We have an underlying data set X that arrives sequentially, like so. And the goal is to evaluate or approximate some given function using space that's sublinear in the size n of the data set. And for us, again, we're going to be a bit more demanding and just do this in log n space. OK, so now hopefully, this whole sentence should be crystal clear. OK, so our main results are for an insertion-only stream, which is exactly the example that you saw on the previous slide, where the points arrive in the data set, and then they never go away. There's one pass algorithm that works for clustering at all times in the stream, and it uses space that is sublinear in log n. And furthermore, these higher order terms match the best known construction. Well, I guess almost the best known construction. In fact, for those who are familiar with coresets, our algorithm actually outputs a 1 plus epsilon coreset construction for all times in the stream. For those of us who are not familiar with coresets, you will be in a few slides. OK, so there's a related model, which is insertion deletion. And in that setting, your points can arrive. And at some later point, they could disappear. And this model is often more difficult. And indeed, we show that if we want a constant factor approximation, there is a separation. So even if you just want a 2 approximation, if you want to do this for all times in the stream, then you need to use log squared n bits of space. I should say that in the previous model, we're saying that this is words of space. So if we're looking at bit complexity, there's still log n or log delta in the dependency, and this is often necessary to store just the points. OK, so for dynamic streams, if we want a constant factor approximation at all times, log squared. And furthermore, if we want to do this from a weighted subset of the input, we also need log squared. OK, so that seems a bit pessimistic. So we show that for 2 passes over the insertion deletion stream, we can actually get an algorithm that does use little o of log n space. All right, so this also shows a separation between 1 and 2 passes. This may not be surprising because there's been a lot of beautiful work that shows that you can do a lot more interesting things when you're allowed more passes over the stream. And finally, I'd like to mention that one of the structural results that we gave is a sum of the so-called online sensitivities, which I'll also go over in a bit. But we see that the sum of the online sensitivities of a set of endpoints is at most k log squared. And this is useful in other applications. For example, if you're familiar with the sliding window model, it's been shown recently that you can view the sliding window model as like a reverse online sensitivity. So this actually gives an easy algorithm for 1 plus epsilon approximation for clustering in the sliding window model. It doesn't give the optimal one, but even the first 1 plus epsilon result was just shown at SOTA last year. So this gives a much simpler approach. OK, so those are our results. And now, as promised, I'll talk about what a coreset is. So if you have a set X, that is our data set. A coreset is a subset X prime of representative points of X. And the goal, of course, is that the cost of a set of centers C on X prime should be roughly the cost of C on the original data set X. Okay. And this should actually hold for all sets of centers C that have k points. So this is what's known as a strong coreset. So pictorially, this is what it looks like. Have a set of points. And we choose a weighted subset of these points, right? So maybe we choose 1 point here, 2 points here, so on and so forth. So here, the red points would be the coreset. And this is one notion of what it means for the cost of the original data set to be preserved. So I should mention that for coresets, if we want anything interesting, if we want to subset sample like a smaller set of points, then they need to be weighted, right? So this is actually a weighted cost. OK, so what's known about coresets is that actually there exist coreset constructions that only require k over epsilon squared times, let's say for the purposes of our talk, k squared over epsilon squared points, weighted points of the input, right? So this is a result by Cohen and Dodd, Casper over there, and some others. In fact, this has been improved. There's a result that gets, I think, k to the 3/2 over epsilon squared. But the key point is that this is independent of the input size n. Okay, so this result is telling us that there exists some subset of the input that is completely independent of the original input size. And somehow it preserves all the important properties of the input size that we care about. And so hopefully this makes more sense as motivation for why I want to study this in the streaming model. See some furrowed brows. Any questions?
Yeah, so here, any course that you can just use it in the streaming like immediately, and it will give you some wow, just create this merge.
Yes, that is exactly correct. So I will, OK, it's not the next slide, but in a few slides, you can use it. But because you have this merge tree that you're talking about, you'll lose log factors.
Oh, log and factors.
You're remembering what Z stands for here?
Oh, Z is the power of like clustering, how much we scale each cost by, the exponent. So I guess if it makes things easier, you should think of z as either 1 for k median or z equals 2 for k means.
Thank you.
Okay. Any other questions? Okay, so if not, then we'll talk about exactly what Sepper is asking, which is what you can do with these coreset constructions in a stream. And there's a popular framework that's known as merge and reduce. And what it does is the following. So suppose there exists a 1 plus epsilon coreset construction for k-means. There is because, well, I just showed it to you in the previous slide. And it uses some function of weighted input points. And like I said before, you can think of this as k squared over epsilon squared, even though that's not the most optimal. So what we're going to do is we're going to partition the stream into blocks that contain roughly k squared over epsilon squared points. Okay. And now the point is that we're going to look at each block and make a coreset on that block. And because that block is exactly the number of points in the coreset, well, the coreset is the entire set of points. And now, once we have a coreset for each block, then what we can do is we can take 2 consecutive blocks, take the coresets for those blocks, put them together. That's another set of weighted points. And then rescale by running another coreset algorithm on this union of weighted points. So putting these 2 coresets together is the merge part of the merge and reduce. And then running the coreset algorithm afterwards on the union is the reduce part. And Sepper said the words exactly like there's this binary tree, and here it is. So you have the stream at the bottom, you break it up into blocks, and then you run this binary tree. Right? And the coreset at the top is going to be the coreset for the entire stream. Because we have accuracy 1 plus epsilon over log n, right? This is where the log n over n comes from. So we have a finer accuracy for each coreset. Then as we scale up to log n levels, we're going to lose this factor like roughly log n times. But this is still going to be roughly 1 plus epsilon. So that's a very simple way of getting a streaming algorithm for clustering if you have a coreset construction. And of course, this applies to other things besides clustering if you also have coreset constructions. Like there are a lot of things in linear algebra, regression that's often useful when you have coreset construction. Yes?
N at the start of the problem.
Let's say you know an upper bound on n. Okay. So yeah, for k-means clustering, if you take all these calculations, this is roughly like k squared over epsilon squared. So we do lose some of these log factors. And you can imagine situations where k is small and epsilon is constant. The n factor could really blow up the overall space usage. Okay. So yeah, like I said, this is where the k squared epsilon squared comes from. So now this really motivates our question, like, can we beat these standard techniques? Do there exist streaming algorithms that use little o of log n words of space? So our result, I guess, again, is yes. There's been a long line of works that all have these log n dependencies. So what we actually do is we first show this online sensitivity sampling technique right here. Right, so that still has a log n dependency. It beats a lot of the previous known bounds. It's really simple, but then we also use it we feed it into our ultimate algorithm. Okay, so that is the background. And next I'll talk about insertion-only streams. Maybe I'll stop really briefly again, ask for questions. Oh, great. Okay, so the question was, what is the output again? And Cam is perfectly right. If we want to output like the actual clustering of the points, there's no way we can do that in sublinear space. So what we want to output is the centers for the clustering.
Okay, so it's not like some online assignment to these centers.
It is not an online assignment, right? At the end of the stream, I'll give you k point, or I guess at every point in time, I'll give you k points. And these k points will be pretty close to the optimal set of centers that you can do.
Okay, thanks.
Okay. All right, so if there are no more questions, then we'll talk about coreset constructions and sampling. And this is something that Piotr alluded to yesterday. So he said that if you've seen importance sampling, this is all pretty standard. And well, here's importance sampling. OK, so consider a fixed set X. So that's our data set. And a set of C that's also fixed of K centers. So it's going to induce some fixed cost, which I'll denote here. And we would like to approximate this cost, right? So again, here we have a set of points in yellow, and the triangles are the centers. So K equals 3 here. OK, so a simple way to obtain X prime is just to uniformly sample points of X into X prime. So we get a subset of points afterwards. That will have the right expectation. Depending on the number of samples you take, that could have really high variance. And indeed, if there's a point out here, this is going to contribute most of the cost to this clustering, right? Because each of these points is not going to contribute that much cost. So unless we sample this point, we're not going to get a good approximation of this fixed cost. But of course, we're smarter than that. We know that uniform sampling is almost never the way to go. So instead, we do importance sampling. And so we sample each point with probability proportional to its cost. Okay, so this set of points will induce some fixed costs. And this particular point will induce a fixed cost. So we're going to sample this point with probability proportional to the ratio of how much this point induces versus the overall cost. And you can imagine that if points are more important because they contribute more to the cost, then we're obviously sampling these points with higher probability. So this ratio right here is known as the sensitivity of the point. And importance sampling needs X prime to have size only roughly 1 over epsilon squared to achieve a 1 plus epsilon approximation. And this is because we have a fixed set of centers C. Now, the problem is that we could have a different choice of K centers. So if we actually move this center from this original partition over here to this point right here, suddenly this point no longer looks important. And remember, for clustering, we actually want to do this for all possible sets of centers because we want to recover the optimal set of centers. OK, so instead of looking at this ratio for one such set of centers, we're going to look at this ratio for all possible sets of centers. So this max C here should be over all possible choices of C, where the cardinality of C is at most K. And this is known as the sensitivity of point X. OK, so if we want to handle all possible sets of K centers, there are two things we need to do. First, we need to generalize the sampling probability to this notion of sensitivity sampling. And then afterwards, we still need to, so then we have correctness for one set of centers. We still need to union bound over a net of all possible sets of K centers. OK. And it turns out that the net size is roughly n delta over epsilon kb. So even if we take a union bound over this, we'll incur log n dependencies here. Okay, so I don't know how to do importance sampling or sensitivity sampling without a log n dependency. Yeah. OK, so again, this is the sensitivity of the point X. And if we take the sum of these values over all the points in the data set, that gives us a notion of how many points we expect to sample overall, because we're sampling each point with probability proportional to its sensitivity. So the expected number of total points is roughly the total sensitivity. So this quantity gives us intuition on how many points will be sampled into the set X prime. So that's good and everything. But for us, there's a problem with this framework, right? This requires us to actually know the entire data set X in advance to calculate the sensitivity of a point. But we get these points in a stream, so we can't do this. Fortunately, there's a related notion called online sensitivity. I think one of the first contexts it was considered was in regression by Kamen authors. So instead of looking at the contribution of a point to the overall data set in terms of cost, we look at the ratio of the point to the overall data set that has arrived so far. So how far a point is with respect to the prefix of points that have arrived. So you can tell immediately that the online sensitivity is bigger than the overall sensitivity. But how much bigger can it be? Okay, so again, the online sensitivity is the same ratio, but now this point here, the denominator is xt. It's the cost of the set of centers with respect to the first t points. Okay, so the algorithm is simple. We're just going to sample each point with probability proportional to its online sensitivity. And there's still two issues, though. Like, first of all, how do we compute the online sensitivity? And then second, what is the sum of the online sensitivities? OK, so if we have a coreset, if we have a 1 plus epsilon coreset, which is ultimately our goal, but let's suppose for some reason that we have one, then I claim we can actually use the coreset to obtain approximation to the sensitivity. And this is because the coreset is already promising us that for any choice of k centers, it's going to preserve the cost up to 1 plus epsilon approximation. So this coreset is already going to give us what's in the denominator of this quantity right here. So by the way, I didn't mention this. Clustering is quite hard. There are results that say that it's NP hard to even approximate. So we're not going to care about runtime in this talk, OK? So now if you have this coreset, what we can do is we can brute force over all choices of our k centers until we find a quantity that is maximal. And that will give us our online sensitivity. So now we can kind of do this in lockstep. Like I claim that if I am doing online sensitivity sampling, I'll have a coreset of the first like t minus 1 points. I have a coreset, so now I can use this coreset to compute the next probability, sample it, and then I'll have a coreset of the first t points, and so on and so forth. Right? OK, so this is pretty standard. Yeah, the whole claim is that we can just do this online. Okay. And given our new bounds on total sensitivity, I claim that the overall coreset size is k squared d over epsilon squared. And unfortunately, we're losing poly n factors here. So it's a simple algorithm. It doesn't give us our goal, but it gives us new understanding on the structure of these problems. Okay. All right. So how big can these total sensitivities be? Well, I guess the spoiler alert is that the total sensitivity is at most like kd-ish. But let's look at an example. So if we have a set of 7 points and 6 centers, then if we choose our centers like so, then this point has sensitivity 1 because this thing is the entire cost. Right? These points each contribute cost 0. This thing contributes cost non-zero, so it has sensitivity 1. Now let's shift the centers around, and you can see that this point also has sensitivity 1, so on and so forth. Right, so it's easy to see that the total sensitivity can be at least k, because here we have k plus 1 points in k centers. Each point has sensitivity 1, okay, or order k. All right, but how large can it be? And it turns out we can do some math, but the point is that if we have a set of points and a set of centers, so these are clearly not the optimal centers, but they still could be the value at which the online sensitivity is realized, in the sense that maybe even though these are suboptimal centers, maybe these are the choices for which this maximum is obtained. Now, there's a simple charging argument. So here is the ratio. This is, let's say we consider the ratio for this point. Here's the distance between this point and the center. So that's the quantity in the numerator. And let's suppose that these are the optimal centers, the stars. So there's a simple charging argument. We can do a triangle inequality, and we can partition the sum of the sensitivities by each cluster. So I can say that, I can consider this ratio for just the points x in this in this cluster that's defined by the optimal set. And the sum of the ratios for each partition will be at most 1. And then there are k clusters. So this goes to show that the overall sums can be at most order k. So what's happening here is what we're really doing is we're saying that there's partitioning, a natural partitioning that's defined by the optimal choice of the centers. And once we have this partitioning, then we consider the ratios in each of these partitionings and show that each cluster has the sums at most 1. And since there are k clusters, then the sum of the sensitivities is at most order k. So this is an offline setting. In online setting, things can be worse because the points are arriving over time. But you can do some simple tricks, like you can divide the stream into times where the overall clustering cost doubles. This will give you 1 log n. And then you can also think of how much contribution a point can contribute within a period of time when the optimal clustering cost doubles. And that gives you another log n. OK, so what's the point of all of this? Well, we can perform online sensitivity sampling. And this will give us a new stream, x prime, right? X prime you could think of as just the points that we sampled. So this stream will have points like k squared, d squared, epsilon squared, whatever, like some factors in k, d, epsilon, 1 over epsilon, and polylog n delta, right? And now we can do the same trick that we did before. We can run merge and reduce. And the point was that merge and reduce incurred these log factors, because we have the binary tree, incurred these log factors in the length of the stream. But now we have this new artificial stream that doesn't have an n factor. There are no polynomial n factors in the length of the stream. It's just polylog n. So the polylog n factors will be polylog n factors here. OK? So this algorithm is super simple, and it does exactly what we wanted. So the new stream has small length, runs merge and reduce, and then overall, the total space is going to be small. OK, pretty simple algorithm, nice warm-up. Questions? Yeah. Big way.
So why cannot do this like online sensitivity sampling again?
Why not do the online sensitivity sampling again? Because so you can do this again to get factors of just polylog n. But because you need to union bound over the net, we didn't do this because you'll lose like k d factors. So if your goal is just to achieve little of log n, which I guess was our original goal, then what you said works. Yeah.
Thank you.
So we just want to be slightly more ambitious and get like the optimal factors here as well. Raf.
Not sure if this is the exact same question or not, but basically, can you just do this more and more layers? Can you get like polylog star of n by taking your now merge reduce stream and then merge reducing that again?
You can't get OK, so you can't get polylog factors because, well, you'll always have the k squared d log epsilon squared. Oh, you're asking about polylog star factors in,
Yeah,
in
so,
n. Yeah, it's a good question. I don't see why not.
I don't think you can chain like merge and reduce because it's not. I think it's important that online sensitivity is just add in points one at a time so it produces a stream. Whereas merge and reduce would add and remove points. So.
Well, I think he's asking about online sensitivity sampling, not merge and reduce.
What does that mean?
Oh, sorry. For online sensitivity sampling, when you sample points, they'll be the sensitivities will be higher. So like after a while, all the points will have like sensitivity, really high sensitivity. So you sample all of them pretty much.
Oh, okay. Gotcha. Cool. Thanks.
Yeah.
So this analysis clearly depends upon your data being Euclidean, but can you translate any part of this algorithm or the algorithm framework to like non-Euclidean data, like maybe your data is like sequences of symbols with a Levenstein distance or something? Or does it like fundamentally violate some tricks you're using?
Yeah, it's a good question. Well, I guess the first thing that comes to mind is that our proof for the sum of the online sensitivities really relied on the fact that our data is Euclidean because we do these triangle inequalities. So you'll still have triangle inequalities, but I guess the question is how much distortion you'll get. I don't see the answer to your question right now, but we do talk afterwards.
Okay. Thank you.
So given a set of endpoints, can you give any advice as to how to choose the proper value of k?
No, I think that's a complete orthogonal question. Choosing the right value of k, especially in a stream, I don't see how to do. I mean, I guess there are these popular elbow methods for seeing. You look at these various values of k and see which one gives you like the most difference.
Because
But,
you have to iterate, basically.
Yeah, I don't see
guess
a way of doing this for a stream. I mean, if you have an upper bound, you can do all these simultaneously. Like if you have an upper bound on what you think could be k, you can do this simultaneously for all these values. But if you don't have an upper bound, I don't see a way of doing this. Especially because the order of the stream can be adversarial. It can be arbitrary. So maybe what you think is the right value of k is suddenly not the right value of k because you get more information towards the end of the stream.
So if you do that, like if you do have an upper value bound for the value of k, is your like overhead just k, or can you do something like cheaper than like just doing like k copies of this, one for each setting of k?
No, I think your upper bound, I mean, it'll still be k because for the highest value of k, then you still need to sample all these things.
Sorry, what I mean is like when you do it for the highest value of k, do you have?
Are you running k copies in parallel?
Yeah, exactly. Do you have to run like fully like k copies in parallel, like for like settings of k from like 1 to like upper bound, or can you like save
your question
on
is
that?
like whether we need to gain an additional factor of k.
Yeah.
I don't think so. I guess it's a question of whether these sensitivity values are monotone as k goes up. I think they should be. I think, yeah, and if they are, then you don't need to do this. You can just choose your highest value of k, and then those sampling probabilities will dominate what you would have chosen for the other ones. Yeah.
So does this algorithm use all k given? Well, I'm thinking about that. Suppose the original data has 5 clusters, and you give it like k of 7, so it will still use all 7.
So I
Or
guess
can it
yeah.
tell me, okay, 5 is enough, so we didn't use all of them?
So at the end of the stream, it'll give you a coreset. So it'll give you a weighted subset of points that will give you a good approximate of any set of centers. So then if you want, you can look at this set of points at the end and say, all right, now I'm going to set k equals 5. What is the optimal cost here? Then I can set k equals 7. What is the optimal cost here? And this data structure will allow you to make all these queries and still be accurate across various values of k
So you're
and various
saying
choices
that,
of centers.
so you're saying that in post-processing, we can sort of reduce that to the minimal, really necessary centers.
I am saying that we can run the elbow method post-processing. That's right, as long as we have an upper bound on k, like the value that we want.
Thanks.
Okay, so if there are no more questions, then we'll go into k-median on dynamic streams. And I'd like to just mention that what I said pretty much doesn't work for dynamic streams, because if we do online sensitivity sampling, if we sample something, then it goes away, then we're pretty much in trouble. Right? So we need some new frameworks altogether, but at the same time, there are some observations we can make that still make the first part of the talk relevant. Okay, so one thing we can do is we can generalize this notion of sensitivity so that each point has a sensitivity, even if it's not in the original data set. And now this could be bad because we have no idea what the sum of the sensitivities are. But the point is that if we sample some of these points with probability proportional to this mystical quantity, and then the point goes away, then if as long as we still sample the original points with the right probability, we'll be OK. So what we're going to do is we're going to use the first pass of the stream to set up some data structure that will allow us to estimate the sensitivity of each point in the stream. And then in the second pass, we won't perform sensitivity sampling, but we'll essentially simulate it in some way. Okay. All right. So just as a reminder, sensitivity sampling is this ratio that we all know and maybe love by now. So I promise you that if we have an approximate set of centers that are near optimal, so let's suppose that S is it's a weighted set, but if it's a weighted set of K centers that's near optimal, then I can use this to find the sensitivities of each point roughly. In other words, rather than have the cost of point X, instead of having this ratio, instead of having the cost of the entire data set X with respect to a set of centers C, once I know S, then I can break down this denominator. And the point is, for each query, I can compute this denominator explicitly. Fun.
So I think I'm confused by what's stated in the claim, because in the definition of S of X, there's a max over C.
Yes.
In the claim, there's just a C.
Yes.
So what do you mean there?
OK. So I should say that this quantity is a good approximation of this quantity without the max. And so if we maximize over all of these quantities, then we'll be able to get a good approximation of the true sensitivity. So we still don't care about runtime. So what we're going to do is we're going to find this S, and then we're going to compute this value for all possible sets of centers. And then we'll take, again, the quantity that maximizes this ratio. OK, so there's a little bit of math. I'll skip this part in the interest of time, but it's nothing more than just triangle inequality and the optimality of the choice of S. So in short, if we can use the first pass to find a near optimal set of centers, and the weights assigned to each of these centers, then in the second pass, we can figure out what is the probability that we should sample each point. Now, how do we do this? We can't use this sampling procedure anymore. We can't use merge and reduce. So it turns out that another popular method in these clustering problems is Quadtree embedding. Piotr talked about this a bit yesterday. So we have a set of points. We're just going to build a grid over this. So remember again that the aspect ratio is delta, meaning that each of these points in any direction is separated by at most delta. So let's build a box around these points with a side length delta. We'll shift this randomly to make sure that there aren't any adversarial dependencies. And now all we do is we just look at the number of points inside this grid. Okay, so this is probably either 18 or 17. Okay. And now we do this for multiple dimensions or multiple layers. So we split it again, so on and so forth. So I think Piotr talked about this yesterday in the context of runtime. What we're actually going to do is use this in the context of space. So one thing you can do is you can view this grid, and all you care about is the number of points inside each cell in each grid at each level. Okay, so you have a frequency vector of dimension 1. You have a frequency vector of dimension 4, or 2 to the d, so on and so forth. OK, so why is the Quadtree embedding useful? Well, let's suppose we have a set of weighted centers. So that means that we think that 6 points will be assigned to the center, 7 points will be assigned to this center, 6 points will be assigned to this center. The quadtree will tell us a good approximation of the cost of this clustering. So all the points are within this box at the top, so the cost induced is 0. Now we have the split, and there are 6 points here in this cell, and there's capacity 6 here, so there's no cost induced by this cell, similarly here. But now here we're in trouble, right? Because this cell has capacity 7, and this cell has cost 7. So this level will induce a cost of 7, which is the difference of these things, times delta over 2. Okay. And we can do this so on and so forth. Now the point is that this cost is just a sum of the differences of the values in each cell. So if you think of this as a frequency vector, or 2 frequency vectors, it's the L1 norm of the difference of the frequency vectors, up to some scaling where you multiply by the grid. Okay, so the quadtree embedding will give us some distortion. But the ultimate goal is that we're going to be able to embed this quadtree into an L1 embedding, and there are algorithms known for approximating L1 in a stream. Right, so they're better embeddings than the one I just showed, but the point is that this one will have a slightly worse space, or sorry, slightly worse accuracy, but better space. So if you don't want some of these terms, you can use a bit more space and be a bit more accurate. Okay, so the point is that the quadtree embedding produces a vector dimension delta to the d. And again, I've already mentioned how this can be viewed as an L1 of the frequency vector. And there exist streaming algorithms that are allowing you to approximate the L1 of the frequency vector, and it uses log space. So log here will be d log delta for us. We don't care about the log delta because it goes into the words. Okay, so the algorithm is pretty simple for those of you who remember. All you do is just generate a number of Cauchy random variables. You take the dot product of the frequency vector with these Cauchy random variables. You take the median, and that's going to be a good approximation of the L1. Okay. So by putting these two things together, first I have this EMD embedding, this quadtree embedding, and then an L1 norm approximation algorithm on top of that. We get a one-pass streaming algorithm that outputs a z such that z is close to the EMD here. And really what you should view the EMD is the optimal cost of the clustering. I kind of changed the notations a bit, but this is the optimal cost of the clustering. And remember, why did we care about the optimal cost of the clustering? It's because this will allow us to compute the sensitivities of each point. Okay. So yeah, we generalized some previous work to show that it suffices to union bound over a smaller net. But the point is now there's a certain sketch size that is using less than log n words of space, and allows to find a good approximation to the optimal cost along with the centers that induce this cost. Okay, so the summary is as follows. There's some streaming algorithm that will give us a good capacitated set of centers along with an approximation of its costs, and that will allow us to estimate the sensitivities of all points. Okay, so pass 1, we're done. We can estimate the sensitivities of all points. What do we do for pass 2? We still can't really do sensitivity sampling because if we sample each point, it can be deleted. But if we do know that if we do sensitivity sampling, things will be sparse. There will be only like roughly kd points that we sample. So what we should do is not sample points of the data stream, but sample points from the overall universe. Okay. So we say that for each point in the universe, we're going to include it in like a substream with a probability that roughly can be interpreted as its sensitivity. And this universe will be pretty sparse in terms of the number of points that are in this universe that actually arrive in the stream. Because if they're too much, then this violates the bounds that we computed for the total sensitivity. And so we can just run sparse recovery on this second stream. So again, we have an implicit stream. We'll have a small number of points at the end of the stream, and so we just run sparse recovery. Okay, so I'll skip over this since in the interest of time, but it's just an algorithm that talks about the guarantees of sparse recovery. But our entire algorithm is as follows. First pass, we set up the EMD sketch. What does that mean? That means we have this Quadtree embedding, we have the L1 sketch on top of that, and then we have a procedure that allows us to recover a near optimal set of centers. That's the first pass. Second pass, we sample elements with probability proportional to their sensitivities into this artificial stream, and then run sparse recovery methods. So that is questions. Yes.
Forgive, it seems like a dumb question, but this is a stream of points that is dynamic, that it means there's possible deletions.
Yes,
in
there
the
are possible
s-
deletions in the
Right
stream.
now, so when are these deletions occurring?
Oh, these deletions can occur whenever the stream demands. Let's just say that the stream is consistent so that it won't try to delete a point that hasn't been added yet. But yeah, your stream could be, I'm going to insert this point over here. Then I'm going to insert this point over here. Now I'm going to delete this first point, so on and so forth.
So
it could be an
I'm
arbitrary
talking
order.
about your process. You first do one pass.
Yeah.
And then before you do the second pass, are there deletions?
There are deletions in the first pass, interleaved within the first pass.
Interleaved at any time in the first pass?
Anytime.
And also in the second pass?
The second pass we're going to say is, I guess it doesn't even need to be the same order as the first pass. Yeah, it's the same stream. It is the same stream.
Okay, thanks.
So in the insertion deletion stream, is the basic reason that you avoid the log n barrier, again, because you're sort of doing this like simulated implicit stream layer, or what part of this allows you to avoid the log n part?
Okay, so there are a couple of things. The first is that this embedding is allowing us to avoid the log n dependency. Like this Quadtree embedding, it's not accurate, but it only has log n bits of space. And same with the L1 sketch and the sparse recovery. And then in the second pass, it's like we're doing sensitivity sampling without.
Okay. So the second pass part is sort of the same intuition as the insertion only part as to why it avoids log n.
No, it's like an
okay.
offline version now. Because we know the sensitivities, whereas the first pass in one pass, it's like an online version, and the sum of the online ones incurs log n factors. Offline, we don't have these dependencies. So it's the correct intuition, I guess, is that the second pass can be used to simulate offline sensitivity sampling, where you already have an estimation of your whole data set.
Cool, thank you.
Does your lower bound also hold if the stream is structured in the sense that, like, first it's only insertions and then only deletions?
Does our lower bound hold in the case where it's only first insertions and then only deletions? Yes. In fact, that is exactly our construction. Yeah.
Is it order sensitive?
Order sensitive in what sense? Sorry, the question was, is the lower bound order sensitive?
Well, is the algorithm order sensitive?
Oh, the algorithm is not order sensitive. It needs to be able to handle any order.
So any order, the
Yes.
same guarantee.
Yes, the same guarantee.
And I still keep thinking about figuring out sort of optimal K. So we don't know how many clusters are there.
We do not know.
So if we give it k which is too large, which means the core set is redundant. So you're saying we can sort of randomly try to remove some points and see if cost blows up or something.
Well, if k is too large, all it means is that we have a bigger core set than we need.
Right. So how can we figure out the optimal k? So remove the redundancy, let's say.
Oh, well, one way to do this would be to evaluate the core set on different values of k, figure out which optimal value of k you want, and then you can still run a core set algorithm for that value of k afterwards.
Yeah, and can we at least detect this situation when k was not enough? So okay, here's your k size core set, but you really need to bump it up.
When k is not enough,
There are more clusters in the data.
there are more clusters.
Can you please give us some indication that this happened?
No, I don't see a way of doing this. Yeah, I don't see a way of doing this because even our estimators have some dependency in k. So if your value of k is too large, I don't see a way of estimating clustering for like a bigger value of k.
I think it's too small.
If it's too small, yes. If it's if your value of k is too small, I don't see a way of handling this. If your value of k is too large, you might be inefficient in your space, but we can do some post-processing afterwards to figure this out. Okay.
Wait, sorry, just to be clear, if your value of k is too small, and too small means the cost is larger than you wanted or something, I guess you'll notice that because you can see the cost that you got, and you'll just raise a flag.
Can we distinguish this situation then? There are really more clusters in the data, so k was not enough.
Yeah, I guess the question is what permits you to notice that your value of k is too small? Like, is it a hard threshold, or is it like some other, is it like there are some choices of k that suddenly make your clustering costs?
Yeah, we're asking, give us k size core set and possibly a flag saying was it enough or not. Is it like, are we in a bad situation when we missed some cluster?
Yeah, I think the answer to that really depends on what conditions you want to raise this flag with. Right? But yeah, let's take this. It's a question. Okay, so I have 5 minutes left. So I'd just like to remind you about k-median. The two things are step 1, we have this AMD sketch. Step 2, we run sparse recovery. For k-means, the main issue is that Quadtree doesn't work anymore. So this is actually a problem that shows up over and over again. There are a lot of papers that use the Quadtree for k-median, and then for k-means, they need to do something else. So what we do here, first let me talk about why why Quadtrees fail for k-means. The issue is that your distortion really depends on how far away your points are. So if your points are a certain distance away, then when you get separated, they're going to incur a cost that's roughly, for k-median, they're going to incur a cost that's roughly the size of the grid. Okay? So if they're in 2 different cells, like here, the cost is going to be the size of one of these cells. And the probability that they're separated is roughly the distance between these 2 points. Now for k-means, the probability they're separated is still the distance between the 2 points. But the cost now is not the size of the cell, it's the size of the cell squared. And so you can work this probability out and see that they're arbitrarily bad distortions. Okay. So the Quadtree embedding doesn't work. But the reason it doesn't work is because when pairs of points are too close to the boundary of the hypergrid, meaning that they should be pretty close, but then the hypergrid separates them, the hypergrid thinks that the cost is really high, but the actual cost is really low. So the bad cases really happen when there's a boundary that separates. This is exactly the bad case right here. So to fix this, what we do is say that we have a different construction on the Quadtree. And we're going to do the same thing as before. But when a point is too close to the boundary, what we end up doing is making a copy of this point on the other side. Okay, so we project the center across the boundary of the hypergrid. And now the point is that these things are now in the same cell, so they don't have that much distortion. Now, what's the condition that we do this? The condition is that if the points are within the 1 over d log delta fraction of the side length of the grid. And we need this choice so that we can take a union bound over all log delta hypergrids with different granularities and each of the d dimensions. And the other point is that after we do this, only order k new centers will be created. That's also important. If we have too many centers that are created through this bicriteria method, then the approximation will be bad. Okay, so we still get a decent approximation, but the order of the number of centers is like order k. We can kind of replicate some of our results for EMD sketch to show that there exists a Wasserstein sketch that has some guarantee that's not great, but good enough for our purposes. And it can also be done in sublinear space, sublog space, and handle insertion deletion updates. So now the algorithm should be the same as before. We set up the Wasserstein sketch in the first pass. We run sparse recovery in the second pass. There's some technical issues because the distortion is like log delta, which means we need to sample log delta points. But we fix that by storing like the offsets of the points instead of the actual points. Okay, so I'll skip this. But yeah, so the k-means algorithm is that we set up the Wasserstein sketch first pass. We again run sparse recovery, but what we store is offsets of each of the points from the sets of the centers rather than the actual points themselves. All right, so to summarize things, we give an algorithm for insertion only. We show that this problem is hard for a single pass for insertion deletion. And then we give algorithms for multiple passes for insertion deletion.
We do have time for a couple questions before we start.
So it's a bit of a generic question, but so there's this like merge and reduce technique. It seems to work for most problems, and it almost never gives you optimal bounds. And like for quantile estimation, there's this GK summaries that is doing, if you look at it very far apart, like it's deterministic, but it handles by saying, okay, the merge are, like you get a better guarantee through the tree. You are doing it by doing some sampling and then passing it to this merge and reduce. Is there something generic happening that, like, is there a better merge and reduce technique that you can design that works, let's say, for all these problems?
Is there a better merge and reduce technique that we can do for all of these problems?
Or maybe let's say a recipe that, okay, this problem has a merge and reduce. What do I need to do to make it like not lose all these log factors?
Yeah, I guess that's kind of at the heart of what we're doing in the first pass. Like if we don't want it to lose all these log factors in the stream length, well, I guess the solution is just have a smaller, shorter stream. If you're still demanding that the stream length is going to be close to the original size, I don't see a way of improving merge and reduce. But yeah, I guess if you don't need the stream length to be that much, then writing some algorithm that would shorten the effective stream is basically our message.
Do you know for any of these clustering problems that merge and reduce give you the optimal bounds? Or for any problem that you can prove it is optimal?
So I guess merge and reduce is usually used for a stream, right? So are you asking if it's optimal in a stream?
Yeah.
Well, I guess what we just showed is that's not optimal. So, and I guess these are the problems that I've been thinking the most about. So I don't know of any problems where merge and reduce is optimal.
All right, thank you.
Any other questions for Samson? Then let's take the notes for it.